In this video, we're looking at section 8.6 on power series, and we're starting on page 127 of our workbook. So we've just looked at example 3, and we're going to get into example 4. But before we do that, let's take a look at this box here in our workbook. So in this box, we have some power series or Taylor series representations of some common functions. So you can see here that we have sine of x, cosine x, e to the x, and 1 over 1 minus x, which will come up surprisingly a lot. But if you wanted to compute a Taylor series for one of these functions, you would find that it becomes the Taylor series on the right. So I just have them here to summarize them for you, because in the next part of this section, we're going to look at how to use these formulas for power series to create power series of slightly different functions. But one of our goals at the beginning of this section was to come up with power or Taylor series for certain functions in a quicker or easier way. So using these formulas here is going to help us. And we can just take a moment to appreciate some of these series. So notice we can observe things like sine of x is alternating, plus minus, plus minus. We see that all of the terms on our, or all of the degrees on our terms are odd. And we can compare that to the cosine function, where we again alternate plus minus, plus minus. And now all of the degrees on our terms are even. So there's some neat patterns that we can observe across all of these series, or within each series. Okay, so now in example 4, we're going to see how we can use these power series that were computed for us to write some other power series or determine power series for some other functions in a quicker way. And one other thing I want to note here is that in this box, it's also really awesome because we're given where these series are valid for, i.e., that's the interval of convergence. So it's awesome that sine, cosine, and e to the x, their power series is convergent for all x. And notice this term, this bottom function, 1 over 1 minus x, its series converges only when x is between 1 and negative 1. And we can even take a look at that series and determine why that is. So the series that we get here is just a geometric series where that common ratio is x. And we've seen that if the common ratio, the absolute value, is less than 1, meaning r is less than 1 or bigger than negative 1, then the geometric series converges. So it makes sense that if x falls within negative 1 and 1, our series for 1 over 1 minus x should converge. So that's just a pretty cool note. Okay, so now let's take a look at example 4, part A. So in example 4, part A, we're asked to find a power series for the function f of x equals e to the negative x squared centered at a equals 0. So we can see that this function f of x equals e to the negative x squared, that's the same thing as the function e to the power, where we've just inputted into the power negative x squared, right? And so what we can do is actually feed in to our power series for e to the x. We can feed into the x there negative x squared. When we do that, we can then create a power series for our function e to the negative x squared. So let's take a look and see how this would be done. So I'm going to just write out that power series, but I'm going to leave x kind of open. I'm going to leave some parentheses here. So e to the x following that power series in the above would look like 1 plus the parentheses or whatever I'm going to stick in, plus that parentheses squared over 2 factorial, plus cubed over 3 factorial, plus to the 4th over 4 factorial, etc. So now into that exponent, I'm going to put negative x squared. So everywhere that I have these open parentheses, I'm going to put in negative x squared, negative x squared, negative x squared. So now I've created that power series for the given function, e to the negative x squared. But before we're done, we need to make sure, or we need to clean up what we've just written here and condense it into a form that just looks like summation n equals 0 to infinity of some term. So let's do that by cleaning up what we have written here. And that means I'm going to simplify, multiply out some terms. So when I do that, so my first term is still this 1, then I get minus x squared. Then I get negative x squared squared. So that would just give me a plus x to the 4th over 2 factorial. Then I get negative x squared cubed. So I get negative x squared times negative x squared times negative x squared. So what happens when I do that? Well, 2 of the negatives cancel, but I'll still get 1 negative left. And then I have a product of 1, 2, 3, 4, 5, 6 x's. So it look like negative x to the 6. This next term would be negative minus x to the 6 over 3 factorial. So let's do this again with negative x squared to the 4th. So we see that those 4 negatives would cancel, so I'd get a plus. And then I have x squared to the 4th, which would be x to the 8th over 4 factorial. Now, if I were to do this a couple more times, my next term I'd find would be x to the 10th, negative x to the 10th over 5 factorial. So now we can get a sense of what's happening here in our terms. So we notice that the exponent, and actually I could rewrite 1 here as x to the 0. The exponent on each of my terms is even. And then I'm just alternating my sign, positive, negative, positive, negative. And then I'm dividing out by the factorial of n. So let's go ahead and write out each of those components. So I'm going to take a sum of n equals 0 to infinity. I want to alternate, so I'm going to have my negative 1 there to the power of n. So as my first term is positive, so n negative 1 to the 0 will be positive. And then the term that I'm multiplying by in the numerator is going to be x to the, well, I only have, again, even numbers. So we can ask ourselves, well, when n is 2, how do I get 4? When n is 3, how do I get 6? When n is 4, how do I get 8? When n is 5, how do I get 10? And we can observe that we're just multiplying n by 2. So the x term looks like 2 times n. And then that denominator is just our n factorial. So our power series for e to the negative x squared is equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n over n factorial. And when you're doing this work in your groups or on your written assignment, make sure you're showing these details along the way. Don't just give this last final series and say they're equal. I want to see all of these steps to show that that final series is in fact what you wanted. So now let's continue this example by looking at part B. All right, so in part B, it says to use the first 3 non-zero terms of your power series from part A to approximate the value of the integral from 0 to 1 of e to the negative x squared dx. What is the maximum possible error in your approximation? So we're going to break this up a little bit. And first, just consider that integral of integral of 0 to 1 of e to the negative x squared dx. Okay, so in order to compute this antiderivative of e to the negative x squared, we might have to use some heavy machinery. But because we found this series in part A, we can just integrate this series instead of integrating this function and using some other integration methods. We can just easily compute the integral of each term of the series. So I'm going to set that up and then we'll look at it together. So what I mean is we're going to look at the integral from 0 to 1 of e to the negative x squared dx. But now that's equivalent to the integral from 0 to 1 of the sum n equals 0 to infinity of -1 x to the 2n over n factorial dx. Meaning, if I wrote this series out, it would look like the integral from 0 to 1 of, then I have my terms 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus x to the 8th over 4 factorial minus plus minus plus. And I'm taking the derivative, or not derivative, rather integral. All right. So now we're just taking an integral of this big sum. So what I can do is compute the antiderivative of each term here. So antiderivative of 1 is just x. Antiderivative of negative x squared, remember that's that reverse power rule. So I'm going to add 1 to the exponent and divide by that new 2 plus 1. And I can do this with each term in the integral. So I'm going to say, so where this is equal to, and just note we took the antiderivative of each term. Okay, so when we do that, we get 1 for that first term minus x cubed over 3 plus x to the 5 over 5 times 2 factorial. I still have that 2 factorial in the denominator. That's just a constant. But then that x to the 4th, antiderivative, add 1 to the 4, divide by 4 plus 1. And please pause the video, slow this down, work out these antiderivatives on your own so that you can convince yourself that what we are working out is true. So then I'm going to subtract. So that'll be a negative 7 over 7 times 3 factorial plus 8 to the 9 over 9 times 4 factorial. And then we'll just, etc. Okay, so here are the antiderivatives. We're going to evaluate at 1 and then 0. So notice when I evaluate at 1, I'm just going to get 1s in all of the exponents, or all of the numerators here, because all of these numerators are 1 to a power. 1 to any power is always 1. So I'm going to get 1 minus 1 cubed over 3 plus 1, and I don't even need that cube, as I just said. We just get 1. So plus 1 over 5 times 2 factorial minus 1 over 7 times 3 factorial plus 1 over 9 times 4 factorial, etc. Minus plus minus plus. And so notice now, if I then went, so that was just when x equals 1. If instead, and I hope you saw this error here, so notice the antiderivative of 1 is x. So I'm going to use red so that you can correct your notes too. This should be an x here. But when I plug in x equals 1, I get out 1. Okay, cool. Because why was I startled by that? Is because when x equals 0, notice all of these terms are just 0. So my first time, or the first value, x equals 1, gives me this sum here. But then when I subtract, when x equals 0, I get 0. So we don't even need to consider that. Okay. So a couple things here. So that would mean that this integral would just become this summation that we have written here. But in this problem, part B, it says use just the first 3 non-zero terms of your power series to approximate the value. So let's take a look at those first 3 terms. So the first 3 terms of my power series are going to land me here. So we're going to approximate this integral by just looking at 1 minus 1/3 plus 1 over 5 times 3 factorial. So that's going to be approximately, you can get out your calculator and check me, 0.7667. Okay, so there is our approximation. So there's the answer to that first part of the question. And now, though, the second part says, what is the maximum possible error in your approximation? Well, notice if we back up to here, this big sum that we were computing, we were calculating an alternating series, plus, minus, plus, minus, plus, minus. And what do we know about how well an alternating series approximates our value of a series? Well, we know that the S sub 3 partial sum will be within that B sub n plus 1. So in our case, B sub 4 will be within B sub 4 of the actual convergent value. So I'm going to write that out just so we can recall that. Recall, for alternating series, the actual series value, so the sum itself, minus the nth partial sum is going to be less than the n plus 1 term. And I don't even need absolute value because the B sub i's are all positive. It's that -1 to the n that's going to alternate back and forth. So what does that mean? So for us, this S sub 3, which is 0.7667, will be within B sub 4, which is 1/7 times 3 factorial. If you want to compute that out, it's 0.024. I'll give us some more room there. So 1/7 times 3 factorial, which is 0.024 of the series value. In this case, our series is that integral that we are computing. All right, so there we go. And if we want to state this slightly different, this means that the maximum error of our 0.7667 is 0.024. So again, this value that we found here, 0.7667, is within 0.024 of the actual series value, which in our case is the value of the integral. So our approximation is within 0.024 of the actual value of that integral. Okay, pretty cool stuff. Thanks for watching.